So the next thing that I would like to discuss is the integrity check. So we just said that in cryptography, we want to protect whatever the parties are sending and receiving. And a story of that would be like, again, let's have Alice and Bob. And Alice is sending some message M to Bob. And if we don't protect this communication, nothing would stop Eve here to drop this message and replace that message with M prime and send M prime to Bob rather than message M. So this would be an example of what would happen in a lot of, we are not concerned of Eve being able to see the content of the message. For example, let's say Alice is asking Bob for a date, and she's sending the location for Bob, and Eve, also is thinking that maybe he can get close to Alice. So what he would do is he would basically send another restaurant address to Bob in this example with M prime, and send Bob away to somewhere else. So this could be an example. If I think it would help you to remember this situation better. So we need to do something here. We need to make sure that when Alice share the restaurant to the address with Bob, somebody like Eve shouldn't be able to change it to some arbitrary restaurant, or at least Bob should be able to detect that, okay, something has changed, so this information is incorrect, or detect this situation. In order to do that, we use something called message authentication code, or in short, we call it MAC. And it is a tag. It is a very small, piece of information that we were sending along with the message to ensure that, the message has not changed. So one of the ways that it can happen is that we can assume that, both parties, they have shared a secret key before, just like the symmetric key cryptography. Alice and Bob already got the key. So if I go and draw this example over here, so we have Alice over here and Bob, and they both know this key K. So now that Alice wants to send this message to Bob, let's for now pretend that we don't want to provide the confidentiality, which means that everybody should be able to see the message on the internet, but nobody should be able to change it. So Alice would send this message M along with the MAC that we call this one M bar over here, that is computed with the hash of key concatenated to message concatenated to key again. So what does that concatenation means? This symbol, let me define it over here. From now on, we would denote it as a concatenation, which means that if you have a letter A concatenate B, then this would give us AB, right? You concatenate two strings, two things together. So right now that we are saying hash of key concatenate to M concatenate to K, that means that we are basically computing the hash of K, M, K, right? That is equivalent to that. The hash function, we would get back to the definition of the hash function in the future, but you can imagine that the hash function, mathematically speaking, is a one-way function that would take an input of any arbitrary binary representation, bits of 0 and 1, but any length, and then it would map it to some fixed amount of bits. For example, if we are talking about SHA-1, the output of this hash function would be only 160 bits. So no matter how small or how large is this message, this M prime would always become 160 bits. So from communication perspective, we are just sending extra 160 bits for any large or a small message that we transmit, and that is something that is acceptable. And once Bob received this information, so what Bob would receive is M and M bar, right? What he would do is that he would do two checks. One, he computes, let's say M star. He supposed that maybe somebody has changed something on the line. So he would go ahead and compute this one as h of hash of key concatenated with M concatenated with key, right? Basically, he will compute that again. And two, he checks if M star is actually equal or not to M bar. And if this condition satisfied, then it means that nobody has changed the message on the line, and the message that he received from Alice is actually the correct message. So you may wonder why this thing could work. The interesting thing here is that, as we said, hash function over here is a cryptographic hash function, and it is a one-way function. So it means that once you have computed this, nobody can recover this key from the output from M bar. And that's a good thing, because only Alice and Bob got this key K, meaning that if now we suppose Eve comes in the game and he wants to change that M to M prime, and then he has to compute that M bar prime now, right, to send it to Bob. This one equals to hash of key that he doesn't know. He has to concatenate it to M prime, and again concatenate it to the key that he doesn't know, right? Meaning that Eve cannot compute this MAC anymore, can't compute the MAC, and therefore he is unable to change that message M. And if he ever changed this M to M bar, then over here Bob would detect that, because when he computes this first line with using M bar, then this M star would never be equal to M bar. I mean, there would be a very, very, very tiny chance that that can happen, but it's negligible. Then it is a very high assurance for Bob that the message that was sent is indeed has not been changed. And again, he is sure that this message is coming from Alice, because why? Because only Alice shared that key with Bob. So if it should be only Alice who was able to compute this correct MAC. Otherwise, you could imagine that maybe Alice shared this key with somebody else, so we can't trust the entire thing. We suppose that they don't share this key with anybody else. And that is the case, though. Bob has two assurances. One, the message is coming from Alice. Two, the message has not changed on the line. This is probably very interesting for you guys to see that how quickly and easily we can protect the integrity of a file or a message that is being transferred online, along with those error correcting codes that the TCP protocol may use. But this has a very different level of assurance and has a very different objective. We don't want to recover the message. The purpose of the CRC codes are to, if we have a few number of errors, we would be able to recover the message. But over here, the purpose is not to recover. The purpose is to detect whether something has changed on the line or not. If something has changed, we would drop it. The Bob wouldn't, trust that message, and he would say, okay, this is not coming from Alice, and he would just drop it. So you see that with the help of a cryptographic hash function and very interesting idea, we are able to provide integrity, and we can go ahead and combine this one with the encryption, so that again we don't let Eve to see the content of the message, but we also wouldn't allow him to change the message or the ciphertext. For now, we're just considering them one at a time, but giving you the idea that in the future, we will come back and combine them to provide a better protection. Any questions so far? All right, if no question, let's continue. A very good example that you could utilize this idea is to protect your files in the system. So if you have ever wondered how a sort of an antivirus system would protect your files and detect if some malicious process has changed the content of your file, is because the antivirus would use the same technology, the same concept. So you imagine that you have file 1, you have file 2, and so on and so forth. So what your antivirus would do, it would store a MAC in a secure way for every file that he find on the system. So he will compute F1, and then he will compute the H1 of this file, right? Where H1 equals to the hash of some, let's say, password, and then concatenated to the binary of this file 1, concatenated to this password again, right? And similarly, he can do the same computation for file 2, where he will get a different hash. Password F2, password again, right? So let's define that here, that PW is, let's call this one to be a protection password. Right? Given that, then the antivirus would go through the files and compute these things, and suppose that only antivirus is aware of this password. So now that your system is up and running, and suddenly some process, and let's say the antivirus is protecting system files. You wouldn't have to protect every single file, but some system files that they should not be changed, configuration files, for example. And suddenly, a malicious process would run in your system and try to change these files. Once the process changed the files, then at least with this technique that you're covering here, your antivirus would be able to detect that, okay, file 1 has changed. Why? Because the signature that I have on this file is not matching anymore, and some process has changed it. Remember that here we are not talking about detecting or rejecting that change. We are just saying that imagine you have this hard disk drive, and then you turn off your system, and then you take out the hard drive, you attach it to some other PC, and happen that in other PC somebody tried to change your some files in your operating system, maybe open a hole in your system for them to get themselves connected to your system in the future. But the point is now that the moment that your system would boot up, the antivirus would go through this check, and it would detect that, okay, somebody has changed this file from the last boot. How do they know that? Because your antivirus would go through this list of Macs, and it would be able to understand that. And what is the storage complexity for this? So we said that every hash function hi, the length of hi is only 160 bits, right? So this is almost nothing, right? With a megabyte of storage, you can cover multiple files, and it has a very little overhead on your storage system. So another objective of cryptography was non-repudiation. And we said that we will come back to this with a better example. I think this is the best moment. So we draw this example and you understand why sometimes non-repudiation is important. So suppose now in this scenario that Bob is a stockbroker. A stockbroker, if you don't know, is a person who would help the clients to buy or sell stocks on their behalf. So Alice is checking the internet and she find out that, the stock of the TSM, which stands for TSMC, Taiwan, is around 81. It's going up. And she immediately sent a message to Bob that, hey, Bob, can you buy me 500 shares of, the New York stock market exchange, TSMC, for the price of $81 each share. And Bob would say, sure, okay, I'll buy that for you. And this happened in some time T1. And after some time, T2 happened, and Alice observed that, the prices of TSMC was going high, but now it just started to decline. And now that Alice has lost some money, she will go back to Bob at sometime T3 and tell Bob that, well, I didn't ask you to buy this stock for me in the first place. Why did you buy it? So this is the best example that, the non-repudiation comes into the game, so that we need to have some mechanism over here to make sure that Alice cannot deny in the future that she sent this message to Bob in the first place. Do you guys have any idea how can Alice achieve this? Or how we can protect Bob against this situation? Do you know what, let me put it this way, do you know what we can add to the system so that Alice is unable to deny that she sent this request to Bob in the first place in time T1? Any ideas? Authenticate the identity of Alice. Yeah, we need to be a bit more specific to that. So, well, Bob authenticate that it was Alice, and then that's why he executed that order. But right now, well, Alice said that she didn't send that message. He doesn't have a proof. Like a timestamp, no, Alicia, I'm afraid that couldn't really help now with the timestamp. Having a log of a user and timestamp, yeah, we are getting to there. So what Nile is suggesting is to have an audit system, a sort of a log system, so that when Alice sends this request to Bob at some point, then we log it in the system, right? But somebody can go and change those logs. So yeah, if you really trust the system, yeah, but yeah, that really doesn't solve the entire thing. Any other ideas? Private key. What do you mean by private key? Is it possible to have a secure login system that tracks interaction and can be accessed by the usual users? So what do you mean by secure login system? You guys are throwing out ideas. It's good, but you need to be a bit more specific. Yes, so finally we get a very good answer. Using digital signature. So imagine when Alice sent this request to Bob, we have Alice to use her, private key to sign this. We said that we have signature scheme. If Alice signed this message and sent it to Bob, then Bob would store this request along with Alice's signature into that, logging system that you guys were talking about and suggested. So later, when Alice would want to deny this, then Bob would go back and say, hey, you send this message and this is your signature. And therefore, you cannot deny that you didn't send this message to me in the first place. Why is it so? Because the only person who is able to sign this message is Alice. So no one else, without knowing Alice's secret key, should be able to create that signature, because we said that the signature schemes are secure. So that being said, signature scheme is a very good example of how we can just simply secure this information, secure this, provide, or let's say provide a non-repudiation. So it was the combination of digital signature and a logging system, right? So let me write it down here for you. So it is a digital.
Just a question.
Mm-hmm.
What if somebody were to just delete the log? Like,
yeah, very good question. So that's where it comes to having a sort of secure log system, right? So you see that when we solve a piece, and I really like this conversation now, that she pointed out a very good thing, that okay, once we have done this, it looked like that Alice cannot deny, but let me expand on her example. What her friend is saying is that maybe Alice has somebody inside the company, and that person would help Alice to go and delete that record on that log system, right? And then Alice would be able to deny again, because there is no record of that request along with the digital signature on the system. And that's right. So do you see, like, it is not very easy to solve this, even these easy examples. And it is, I always encourage you guys, and I stop a lot of time throughout this lecture. Today is just a practice for you guys to speak out and bring up these problems. And so that's why we have to put in parentheses that it has to be secure. Okay, how secure? What are the definitions out there? This is not something that we want to touch now, but we assume that nobody can delete or alter anything from this log system. One of the things that you can imagine of using this secure log system is, like, you can imagine blockchain, for example, right? If you use blockchain, we know that once you put something in blockchain, you can delete it or you can alter it, right? So using blockchain over here instead of as a log system would be a very wise choice, because it would protect us from somebody deleting or altering any information in the past. Any other ideas? If we can limit the secure logs to a set of amount of individual, it would be easy to track, as well as having auditing system for those set of individual. Well, the point is, why do we limit them? Because we might have a lot of users, and all those users, they want to have protection. So it is the best that we don't really limit the system. We want to have non-repudiation against everybody, every user on the system. So you see that, this is actually how the security thing gets solved. Raise the issue, and then we discuss about it. And you see that with 5 minutes of discussion together, we actually came up with a pretty good system now here. It covers most of the threats that I can think of right now. Minor changes that we would just don't need to mention them now. But it is an example of the lecture that I would like to have from now on. I want your contribution, and never be shy of making mistakes. It is fully acceptable for you guys to make a mistake. You are sitting in this class because you want to learn. Without making mistakes, you would never learn. So please don't be shy. Share your idea. The idea that is in your head is maybe is also common with somebody else. And if you speak it out, we can discuss. Maybe it is a very good idea, or maybe it is a very bad idea. You won't lose anything if you share a bad idea. We will all learn from it that, in this situation, this idea was not a good idea, and what was the reason? Okay, so please don't hesitate to share ideas, or if you have any questions with others, because it would help everybody to understand things in a better way. Let me also keep track of the time. Okay. So so we said that, for the non-repudiation, we just discussed that we want to use digital signature. But for some of you that are wondering how the digital signature would work, the digital signature is working just like the public key, but we are just basically using it with the reverse keys. So let me actually give you, let's go through our Alice and Bob. I think that is the best way to help us to understand it better. So again, let's draw this Alice and Bob communication. So imagine that Alice now wants to sign something for Bob. So just like the public key cryptography, digital signature is also a public key. It's developed using a public key. So which means that we would again have a public repository where every user would generate a public key and a private key. So, but the definition of them, we would change them a little bit so that it is easier to understand. So instead of Alice having public key, we say that Alice have verification key, which is the same as public key, but we just want to use verification key to make it clear that this is going to be used for digital signature. So this is for Alice, and we have the secret key for Alice again. And Bob got the same thing. So Bob got verification key for Bob and the secret key for Bob. So just like the public key cryptography, this user, they need to publish their verification key. So verification key of Alice and verification key of Bob. So, and then let's say some random bits, right? And this is accessible in public, and we would get back to that, and nobody can change it, and so on and so forth. And again, there is a mathematical relationship between the verification key and the secret key of every user. And again, by publishing the verification key, nobody can extract the secret key of that user. So it is very safe to publish the verification key. So now that Alice wants to, send that request to Bob, Alice would use the same method, but we would ask her to sign it for Bob. So she's sending that message M, which is the request of her having Bob to buy 500 shares of TSM for the price of 81 per share, and then we would have her to sign it. Normally we use the symbol sigma for the signature, so the sign algorithm. So she would use her secret key of Alice to sign this message M. The reason that we use this one is that, the story with the digital signature is that the user would use, unlike the public key, would use your own secret key to sign. And then Bob would be able to extract your Alice verification key from the public repository and verify that signature. So once Bob received this one, Bob can go ahead and run the verify algorithm. The verify algorithm would take verification key of Alice, which he downloads it from public repository, the message M itself, and the sigma. And then the result of this is to be true or to be a false. That's all what it returned. If it is true, means that this message M is correct, the sigma is the correct signature for M, and it is indeed signed by Alice. So he learns two things at the same time. So the message is indeed coming from Alice. Two, the message has not been altered or changed or modified before it gets to Bob. This is exactly the same message that Alice has sent, right? So this is the story of the digital signature in a very high level. So if you go back to the public key, remember that in public key, what we've done was that when Alice wants to encrypt something and send it to Bob, we use Bob public key, the recipient, and we would use that to encrypt it. But right now, in the world of digital signatures, we won't do that. Alice is sending a message to Bob. Alice should sign it, and Alice should use her own secret key to sign the message in. And Bob, the recipient of the message, would use Alice's public key, which is safe to share with everyone. And with that, he would, be able to verify the message. If this public key, the public key and a secret key is still a bit confusing for you, let me give you a very good example. Imagine your email service. For your email, you have an email address, and for that, you have a secret key that you, set it up when you sign up for that email address. You can always share your email address with everybody, right? Whoever you want to receive a message from. And the fact that you give your email address to somebody, it doesn't mean that they can hack your email address. It's not possible to hack directly from your email address to log into your system, right? Unless if you use very weak passwords and all those stuff. But there's no one-to-one relationship there. So it is always safe for you to share your email address, but you don't want to share your password for that email account, right? So you keep it secret. It is the same concept over here. The verification key or the public key is always your email address. Imagine that you can, publish it. There is no harm for it, unless maybe you get spams. But for your password or your secret key over here, you always want to keep it private. So this is an analogy of what the public key cryptography is based on, if you have a hard time to understand it. So I hope this example would make it easier for you to digest it, that why do we have two keys? So this was the way that we could actually utilize the public key cryptography to do it. We have another concept. Let me change my color, of hash then sign. So do you guys would know what happens if I just continue with this idea of signing the message directly? Anyone would want to point out what happens? Because it seems like that people are suggesting to hash the message before you sign it. And why not I just sign the message itself? Why do I have to get the hash of the message to sign it? Any ideas? Any idea why in the digital signature we want to hash the message and then sign it rather than just signing the message directly? It could be faked. How be faked? Maintain the great integrity. No, it has nothing to do with the integrity here. It is very good point. It could be one of the reasons that we could add randomness to it, but I don't want to bring that subject now. Make it more random to reduce the size. Yes, exactly. This is the answer that I was looking into. So imagine that over here we say that Alice would sign a message, and the message was basically a few lines of text, right? Only this thing. And we were able to do it. But the digital signatures, they accept a message from a space of, maybe few hundred bits. What if you want to sign a file of few gigabytes? What would you do then? And then if you were to sign that huge file, even though your signature scheme would allow you to do it, that would become very computationally expensive. So, and also, the size of the corresponding signature would be quite large. So one of the best practice over here is to hash a message. So we said that when you hash a message, you get maybe 160 bits, right? And that would make sure that no matter how small, we know that the hash functions would always have a fixed output length. So if that is the case, if no matter how small or large is our message to sign, when we apply a hash function first, one of the good benefits is to make sure that the size of the messages that we want to sign is always 160 bits. And when you set up your signature scheme, you can keep an eye on that and choose the right size of keys when you do the key generation. That we will have a lot of discussion about that, so that you can support the fact that you can sign messages of 160 bits length. So this is a very good property that we get once we hash and then sign the message, so that we would be able to basically, no matter small or what kind of key size you get, you are able to always sign a small or huge files at the same time. Pretend as the sender? No, that is not what the hash function would do, because if you see the hash function doesn't take any other parameter, but such as key or something. It just take the message and it would just compute it over the message. If the hash function, we added some key to this, yes, then you will be right. But for this purpose, we are just computing the hash of the message itself, and that hash function is just a one-way function. It just shrink the input, right? So it doesn't really add who did this. We don't add any information like that to this hash function. So, but we have a condition over here that it has the hash function has to be a strong cryptographic hash function. What is a strong cryptographic hash function, or cryptographically strong hash function? It would get to there sooner or later, but it's one of the conditions that you can use any hash function. Remember, you should only use cryptographic hash function. That we would discuss about it a lot, so you would get to know why is it the case. But I can't bring it up, unfortunately, now. Any other questions? All right. Let me see what we are going to discuss. Okay, so we are going to change the trend quite a lot now. So I think I would like to stop the lecture here. I don't want to open a new topic. So today we have spent quite some time. We understood the objectives. That is the most important thing, the objectives of the cryptography. We have covered some examples, and I hope that now it is clear for you guys what is the objective of every goal for cryptography. So in the future, we would come back with even much better solutions. For some of them, we had some minor solutions so far, but we would come back with some better solution that you could see how what are the better algorithms that could help to achieve, let's say, any of these objectives that we've just covered today. I think for the next week, we would go and cover some newer topics, such as the difference between primitives, protocols, and some interesting, we would define who is the adversary, how to prove, and all those interesting things. I think we would just keep it for the next lecture. Any questions, guys? A hash function, we haven't give you the definition of a hash function, but you can imagine that the hash function is a function that has a very huge domain and would map to the range that is very small. So this is the definition of a hash function. Or actually, maybe I should make this one even smaller to a very small. So how the hash functions would do that, we would, when the time comes, you will see the definition and how exactly we would compute that. But in abstract, this is a one-way function. So this is, I think, in abstract, the best way I can explain it to you, that it always take values from huge sets and it would map it to a smaller set. So since we have a smaller values on this set, so we can have a efficient encoding for those values, and that's why we have fewer bits, maybe 160 bits over here. And we can represent all these values on the range with only 160 bits. But over here, we need a huge amount of bits to represent all the elements in the domain set. If there's no other question, so the class is dismissed, and we'll see you guys next week.